You know those massive, loud, clanking tunnel machines in hospitals? Yeah, the MRI. Maybe you've even been inside one yourself. But what's actually happening behind the scenes of that machine is, quite frankly, nothing short of miraculous. Today, in this explainer, we're going to completely demystify one of the most remarkable technologies in modern medicine. I mean, think about the historical stakes for a second. What if doctors could see inside the human body without making a single cut? For centuries, that was the ultimate holy grail of medicine. Before this, doctors basically had to rely on feeling around, guesswork, or, invasive surgery just to see what was going on. The stakes were incredibly high, and the need for a safe, non-invasive window into the body was absolutely massive. So here's our roadmap for this explainer. We're going to cover beyond the X-ray, the spinning atomic magnets, from signals to pictures, exactly how an MRI works, and finally, a medical revolution. Let's get right into it. Section 1. Beyond the X-ray. Now, X-rays were an absolute game changer when they hit the scene, right? Suddenly, finding a hidden bone fracture beneath the skin was easy. But they had a massive limitation. They're really only good for hard structures. Doctors desperately needed a way to see all the squishy stuff, the soft tissues, like brains, muscles, nerves, and organs. And X-rays, they just couldn't deliver that clearly.
Which brings us to Section 2, the spinning atomic magnets.
So how did we solve this? Well, it definitely wasn't an overnight medical invention. Back in the 1930s, physicists stumbled on this quirky phenomenon called nuclear magnetic resonance, or NMR. Fast forward to 1946, and physicists Felix Bloch and Edward Purcell actually demonstrated it in action. That was such a huge deal they won the Nobel Prize in Physics for it. But here's the wild part. It was still just an abstract physics experiment. Nobody was even thinking about medical scanners yet. It wasn't until the 1970s that Raymond Damadian actually started applying this to human tissues. Okay, so what exactly did those early physicists find? They discovered that certain atomic nuclei basically act like tiny spinning magnets. If you put them in a strong magnetic field, they can absorb and then release electromagnetic energy at very specific frequencies. As the decades passed, scientists realized, wait a minute, this bizarre little phenomenon can actually reveal hidden information about the chemical environment right around those atoms. All right, Section 3, from signals to pictures. Now, turning those weird physics signals into an actual detailed picture, that was a massive puzzle. There wasn't just one lone genius yelling Eureka. It was this incredible collaborative journey. You had Raymond Damadian discovering that NMR signals actually differ depending on whether tissue is normal or a tumor. Then, in 1973, Paul Lauterbur had this brilliant idea to use spatial magnetic field gradients to encode exactly where a signal was coming from. And finally, Peter Mansfield stepped in and developed the super-fast mathematical processing needed to convert those abstract signals into actual readable images. Let's move on to Section 4, how an MRI works. Let's demystify the magic trick here. It actually all starts with the number 1. Specifically, the single proton found inside a hydrogen atom. Now, think about it. Our bodies are mostly made of water, right? Which means we are absolutely packed with hydrogen, and each of those single protons acts like a tiny little magnetic object. On a normal day, like right now as you're listening to this, the magnetic fields of those millions of tiny particles in your body are just randomly scattered, pointing in totally different directions. But the second you slide into an MRI scanner, that completely changes. Inside that super strong magnetic field, all those random hydrogen nuclei just snap right to attention and align themselves. But they don't just freeze there perfectly still. They do this thing called precession. It basically means they act a bit like tiny spinning tops, wobbling around the direction of that massive magnetic field. Okay, we can break this crazy complex physics down into 4 distinct, easy-to-remember phases. Step 1. Magnetize. That strong magnetic field aligns your hydrogen atoms. Step 2. Disturb. The machine fires a carefully controlled radio frequency pulse into your body, which temporarily knocks those atoms out of alignment. Step 3. Listen. Once that radio pulse turns off, the nuclei relax back to normal, and as they do, they release extremely weak radio signals. Specialized coils literally listen for this echo. And finally, Step 4. Map. Heavy-duty computers crunch those signals into the highly detailed images doctors use. Now, you might be wondering, if the machine is just picking up a bunch of random radio signals, how on earth does it know exactly where in the body they're coming from? Enter the gradient magnets. These are secondary magnets that tweak the magnetic field strength just slightly, depending on the exact physical location inside the scanner. Because the hydrogen nuclei wobble differently depending on their spot in that varied field, the scanner can pinpoint exactly where each tiny little signal originated. Pretty clever, right? Which brings us to Section 5, a medical revolution. When you look at modern MRIs, what they can do is honestly staggering. They create this incredibly sharp contrast between soft tissues, so doctors can easily spot the difference between muscle, organ tissue, or a tumor. By just tweaking the scan sequence, they can emphasize fluid or highlight fat. But here is the absolute best part: zero ionizing radiation. None. Unlike X-rays or CT scans, an MRI runs entirely on harmless radio waves and superconducting magnets. And get this, those magnets are actually several times stronger than the Earth's own magnetic field. No way, right? But because we're dealing with magnets that powerful, safety is a huge deal. It's why you get asked 1,000,000 times if you have any metal on you before you go in. In a magnetic field that strong, an ordinary metal object can literally become a lethal projectile in the blink of an eye. So strict safety protocols in those rooms are an absolute must. Oh, and while we're talking procedure, you might also be given a harmless fluid called a contrast agent before a scan. That just helps certain blood vessels really pop on the final image. So when you zoom out and look at this whole journey, you realize an MRI is so much more than just a loud piece of medical equipment. It is literally the result of nearly a century of scientific discoveries, technological leaps, and pure engineering genius. It's the ultimate proof of what happens when physics, medicine, engineering, and mathematics all collaborate across decades. If there's one big takeaway from this explainer, it's this: the MRI doesn't see your body with light, and it definitely doesn't require a scalpel. Instead, every single time someone gets a scan, that machine is putting almost 100 years of fundamental physics to work, simply by listening to the water in our bodies. Magnets organize the hydrogen, radio waves give it a nudge, and computers listen for the echo. It's a magnetic miracle. And that leaves us with one incredibly exciting question. What other invisible mysteries of the human body is fundamental physics going to unlock next? As brilliant minds keep pushing the boundaries of medical technology, the possibilities are literally endless. I hope the next time you see one of those clanking, humming machines, you look at it in a whole new light. Catch you in the next explainer.